Still, how many people are in here? 18? That's right, I can get started. If people come in late, that's fine. So today we are going to talk about language-based metaprogramming. So we've been this entire time we've been operating within a language and seeing what kind of meta stuff we can do inside of that language. But now we're going to step back a level and we're going to see what we can do with languages and how we actually deal with languages and how that in and of itself is often a very meta thing. So let's see, I'll go ahead and pull up my slides. Yeah, language metaprogramming. I don't know, I mean, there's probably a more accurate name for what this is, but to me, I feel like it fits into our class because we're going up a level to the level of languages in general. So this isn't a technical term, but that's what we're going to be doing today. First off, I just want to say there was a homework due today, and then there's a homework due next week. Just quick outline of the rest of the class. The last homework is due next week, which is crazy. I've kind of stayed away from saying anything about peer evaluations, peer grading. That's because I didn't really have a strong preference about what people do. But what I've ultimately decided is that I'm going to open up the peer grading for an entire week instead of just for the rest of the day. So if you get a chance, go in and do some peer grading. Again, it's not like I need that peer grading to happen in order to, I'm not going to grade you based on it. But I just think it's good for everybody to get another set of eyes on their code. And the easiest way to do that is to get each other looking at each other's code. So peer evaluation should be open, just do that at a certain point. And if we have time at the end of the lecture today, I'll go over the homework a little bit. Next week is the last lecture. And so my plan is I'm going to go over homoiconicity for a little bit, depending on how much I end up writing about it. And then we'll go over some conclusion. And then we may or may not have a quick in-class final. But the in-class final is mostly just an exit survey so I can get some feedback. But there might also be some general metaprogramming questions, but probably the conclusion that I will have just done will probably answer those questions. So definitely don't stress about that. So anyway, any questions about upcoming schedule outline for the rest of the class? Anything like that? Let's see, I'm curious. I just hit spotlight video. What did that do? Did that do anything to anybody? No, nobody saw a change?
It moved me from screen share to your face.
Oh, that's not what I want. Go back to a screen share. Don't look at my face.
I don't know. I'm enjoying this.
All right. Well, if you can look at my face if you want, but interesting. I didn't know what that button did. So, all right. So slides are up. I would definitely be focusing on slides. All right, let's do it. So language metaprogramming. So we're going to talk a little bit. Oh, I forgot to change the slide. We're not going to talk about homoiconicity today. That's going to be next week. But then we're going to talk about some levels of abstraction, compilers and interpreters, bootstrapping, and then this new thing referred to as a specializer. That's where the really crazy stuff is going to come. And then we're going to talk about compilers, which are exactly as meta as they sound. So let's start. In the beginning, there's just a processor, right? At the end of the day, we like to write these programs in these high-level languages like Python, Java. That's what we've been spending most of our time in. But at the end of the day, it's really just a processor that gets ones and zeros. And that's all we have. So we need ways to get down to machine code. Machine code is what actually executes. And we need ways to be able to abstract from that because nobody likes writing machine code. If you've taken 2150 or are currently taking it, you've probably already done IBCM, which is the machine code assignment. And it's where you have to write a program by just typing in ones and zeros, basically. And then you hit run and that executes. And it's a huge hassle. If you've done that, then you know how hard it is. So let's see what kind of abstractions we've got here. The first one that we're probably all familiar with, and it's what you use in 2150. It's what you use in 2110. It's a compiler. And so here we've got some high level code. This is the kind of code that we like to write. You might not think of it as high level because I think this is C, but it's high level compared to machine code. And just take note of the color coding here. If you put this code into a compiler, what you get is you get an executable version of that code. So the compiler is really just a translator. It translates one language to another language, and often it translates a higher level language into a lower level language that's somehow easier to execute. So in this scenario, this compiler is compiling C into assembly, and assembly isn't machine code, but it's a whole lot closer to machine code. So this is a lot easier to execute. And one cool thing about this here is that the color coding actually matches the color coding of the original. So you can see exactly what lines in the original code got translated into what lines of assembly. This is a really cool tool. When I wrote these slides, it was online at godbolt.org. No idea why it's called that. And it might have moved since I wrote these slides, but very useful for 2150 and computer architecture. So if you're in those classes, cool stuff. So for this lecture, I'm going to refer to compilers with this symbol here. And you'll see why later. It's going to be really handy to have symbols for these machines because we're going to end up putting them together in really cool ways. So a compiler I'm representing with this kind of semi-trapezoid thing. It takes in a program as input and it outputs some translated version of that program. And also just a quick note, compilers don't have to always translate closer to machine code. A lot of people spend a lot of time writing transpilers that compile one language to kind of a sister language, where the goal isn't to become closer to the hardware, it's just to become more compatible, say. So, any questions about compilers on a high level? Okay. So we've got compilers, and then also most people have probably heard of interpreters, especially since we're in a Python class here, we spend a lot of time with interpreters. And so if a compiler translates the program, what does an interpreter do? Does anybody want to offer a definition?
It just follows the program.
Yeah. Yeah, an interpreter just goes line by line, essentially, through your program and just does it as it goes. So a compiler is reading through your program, but outputting program. But an interpreter is going through your program and doing it. So an interpreter doesn't actually output anything except for what your program should output. So let's see that. Yeah, it does not translate, executes on the program's behalf. So we write this program in this high-level language, but then it's actually the interpreter that's running. And you can see this if you ever write a Python script and you run it, and it's a really long Python script, and you look at your activity manager, you'll notice that the program running that's taking up all of your compute resources is not the program that you wrote. It's the Python interpreter. So what you're really running is the Python interpreter. In fact, you can even see that when you run a Python program in the command line. In the command line, you don't run /, then your program. You run Python3, your program. You're actually running the Python interpreter, and your program is just instructions to the Python interpreter. So it's a different kind of model. In the compiler, you compile the program, and then you run the program directly, assuming you've compiled it to machine code. And for this lecture, I'm going to use this symbol to refer to an interpreter. So the last symbol for the compiler, it kind of opened up at the bottom. That's to show that it's outputting like a big chunk of code. Here, the interpreter is just coming down to a point, and that point is the point of execution of the program, where we put a program in, and then the interpreter does it directly. Yeah. Now, it might not seem like it, but the interpreter really always takes in two inputs. The interpreter takes in the program that you're interpreting, and we see that when we run Python 3 file.py, file.py, that's input 1, that's the program. But then the interpreter will also take in whatever other input your program requires. So it's kind of a hidden input to the interpreter, but the interpreter always takes in whatever the program requires too. So you can see here, this is a program on input X. So the interpreter then has to also take in X. And also just a quick thing to note, interpreters are easier to write than compilers. I don't think there's a single exception. So that might become interesting later. Questions about interpreters? Okay. So I'm going to go over some notation that we're going to use here. This little block is some data. And then the triangle is a program. And similar to the interpreter, it comes down to a point because the program just executes. And you can, it doesn't output another big chunk of anything, it just executes. P is for program, and programs may or may not be executable. So like, I'm kind of representing this higher level language program without a funnel at the top. So like, you can imagine this is a program conceptually, but it doesn't actually do anything. It's written in Python maybe or something. With this program, it takes in a funnel, and that's to say this is a program that actually is executable. And you can see the X here means that it takes in X, and then the result of running the program, I'm representing with function notation. So after running program P on X, the result is P of X. So function notation represents running the program. And programs can take in multiple inputs here. So this takes in K and U. And then the result of running on K and U is P of K, U. And then we also saw already compilers and interpreters. And you can kind of see that the interpreter is, the interpreter comes down to a point because it's similar to a program. Running the interpreter does the same thing as the program, but the compiler does not, because the compiler is really just an intermediary step. It outputs yet another program. Okay, the other thing I'm going to do is I'm going to use superscript to refer to the inputs of a program. So an interpreter could always be written as I super px, because it takes in the program that you're interpreting and then whatever that program needs to take in as input x. And then if you call an interpreter, then you call it on p of x, p and x, and you would get the result of px. So does that make sense? Questions about this notation? See, I don't remember if there's another bullet point. There is another bullet point. Yeah, and then I'm representing these kind of boxy inputs for programs. So you can see the interpreter takes in a boxy input for the program funnel. Yeah, it makes sense visually to me. I don't know if it makes sense to other people, but I think it's kind of cool. Okay. So what's the relationship between a compiler and interpreter? Now that we've got this notation, we're using function notation to refer to programs being run. Then what's the relationship between a compiler and an interpreter? Well, let's say we have this program here and it's in a high-level language, and we compile it. We feed it into the compiler, and the output would be a similar program, but that's executable. And so the way we would write that down is that C of P, we've created C of P here. This thing here is C of P. And then if we pass in data to it and run the result, then we would refer to this with another function notation. So C of P is this program here, and by passing more data into it, we're calling it again, we're running it. So using a compiler to run a program is really two program executions. You compile the program and then you run the result. So that's what we're seeing here. Program running the result on the data. Now, how does that relate to using an interpreter? Well, with an interpreter, we've got the same program, but then we feed it directly into the interpreter, and whatever data the program requires, the interpreter takes in. So the interpreter is a function of two inputs, the program and the data, and the result of calling the compiled program is P of D, And the result of interpreting the program on the data is also P of D conceptually. Even though that's not physically what we did, the result is the same, or should be the same. If the compiler and the interpreter are for the same language, then the result should be the same. So we can say that compiling a program and then running it is the same as interpreting the program and the data at the same time. So that's the relationship here. And this is going to come back, this is going to be important later when we start combining these things. Questions about this? All right. So we're going to talk about bootstrapping now. And bootstrapping is all about solving the problem of how you make the first compiler. How do you make the first compiler? Like, let's say we're back in, I don't know, the 60s. I don't know my computing history very well. Alex Hicks would probably know better than me. Let's say we're back and all we've got is assembly or machine code, something like that. And we want to write a higher level language, and we want that higher level language to then be translated back into what we've got, machine code. How would you do that? Well, the only option we have really is to write the compiler in what we have, right? If we want to have some program that translates our high level language into a low level language, we need to actually run that program. So we can't run it in the high level language. We don't have the compiler yet. So we need to write the compiler in some lower level language first. So that's what we see here. We could either start our compiling with some other language and then use the compiler for that language into assembly, or we could start with a compiler in assembly. But either way, we have to start with something we've already got. We've already got some compiler that's written in assembly, or we just have assembly. Either way, we're starting down here. But then we've written this assembly compiler, but what's the problem? The problem is that assembly is hard, and that this compiler is probably not good. I mean, compilers are incredibly complex programs, and having to write one in assembly is mind-blowing, just staggeringly difficult. And so it's not going to be good. It's probably going to have bugs. It's probably going to be slow, and it's probably not going to support a very wide range of features for your language. So what's the solution here? Well, as you can see on the left here, the solution is bootstrapping, and what that involves is hosting your language in itself. So let's say we've already written this compiler in some other language, or we've written the compiler in assembly. What we want to do now is use this language that we've written a simple compiler for it now. We want to rewrite the compiler in its language, which we can do now because we have a compiler that can compile that language. So we write a compiler in our own language, and what do we do with it? Well, we use the compiler that we've already written to compile it, because we have to, right? It's in a high-level language. We can't just run it. It has to be compiled. So this compiler has to be compiled by the compiler we already have. So that's what we see here. We've written the compiler in the language that we're trying to implement, and then we compile it with our more primitive compiler that we already wrote. Okay, so that's pretty cool. Maybe now this time we did a better job. Maybe we did a better job of implementing this compiler because we got to write it in a nice high-level language. So it's probably the case that this compiler is actually better. And so by compiling it, we've ended up with a better compiler for our language. Now here's something that you can do, and I didn't animate it on the slides, but let's say we've actually taken this compiler, and it's a better compiler. We've compiled it through our original compiler, a Bootstrap compiler. We've gotten this improved compiler that's executable. What you can do now is you can recompile your own compiler through that compiled compiler. So at first we compiled this thing with the simple compiler, but now we're going to compile it again with this guy. And since this is a better compiler, we're going to end up with a better version of this better compiler. So there's better writing of the source code of the compiler, and then there's compiling that source code with a better compiler that was resulting from the better source code of your compiler. So we actually get double benefit from this because we've implemented the compiler in its own language. Now let's say we've added some language features in this process here, and so now we can actually improve the compiler again in source code. Then the same thing applies. We take this even better, more fully featured, maybe this one is optimized. Maybe we've now written an optimized compiler. Then we recompile that with our original better compiler, and we have a really advanced compiler. And then of course, because why not, we compile this thing with the advanced compiler just to get an advanced version of that advanced compiler. So this is bootstrapping. And this is how we get to such amazing high-level languages that we have now. None of what we take for granted with Python and other high-level compiled and interpreted languages would be possible without this, our ability to take some good idea and then benefit from it doubly. You can almost see the exponential growth here. You know, making a small improvement in the source code of the compiler, if the compiler is written in its own language, benefits both the compiler and every program that compilers, or the compiler compiles, including itself. So this is surely mind-blowing. I don't know, I struggle to keep it straight in my head, but it can often seem like, how on earth do we get to these great languages? I mean, who sat down and wrote this amazing compiler for C++ 2014 in assembly? That seems impossible. It is impossible. That's not how they do it. You know, you have to work up slowly, build more and more advanced compilers that support more and more complicated features that allow you to then implement more complicated features. So this is bootstrapping. Questions about bootstrapping?
So when we went from C1 to C2, or I guess when we were compiling C2 with C1,
yeah,
we got a couple kind of levels of improvement without rewriting any compiler code, just because we were compiling it with a better compiler. Mm-hmm. Does that keep going for a little while if you keep like recompiling without writing any new compiler code?
I think it only goes twice. You get to compile your better source code with your old compiler, and that gives you a better compiled compiler, which you can then use to compile your compiler again. You know, actually, it probably depends on just what kind of optimizations that compiler does. Now that I think about it, I could totally imagine scenarios where the compiler, every time it compiles itself, it actually unrolls more and more loops or does more and more function inlining in more and more complicated ways. But there would probably be a trade-off. I can imagine a scenario where, yeah, the compiler will do aggressive loop unrolling, let's say. But then if you do this too many times, then you end up getting too aggressive, and the compiler ends up becoming huge. You know, it's possible that you could end up with a compiler that just is like the source, the compiled compiler is so large that it wouldn't fit on anybody's machine. I'm not 100% sure though. I mean, it probably depends on the specifics of the kind of optimization that are being done. Yeah, great question though. Other questions about this? I like my standing desk setup here. Is this distracting? I feel like I'm kind of waving back and forth a lot, but that's what I do in actual class. And I also like having my hands in my pockets, you know. I always have my hands in my pockets in actual lecture, and I got kind of made fun of for that. And so it's nice to be able to put my hands back in my pockets. Okay, let's move on. So we're going to talk about a new thing here. This is partial computation. This might sound familiar because we already kind of did partial computation very early on. We wrote this partial function. I think, did I call it specialize? I think the homework was actually called specializer. And I renamed it because I wanted to draw the connection from that to this. So we wrote this function here and it took in a function and some args, and then it defined a new function which took in more args, combined the args, and then returned the original function with the combined args. So this was a homework earlier. And the way it's called in Python is partial. Turns out this is kind of an interesting idea. For example, let's take this function, f of ku equals, then we've got this complicated thing, k times k plus 1, all in parentheses, plus u plus 1, all in parentheses. Some mathematical expression. You can think of this as a program. I mean, it's just a mathematical expression, but the way it would end up getting interpreted or compiled would be a set of instructions. You know, this would be take k, load k, add 1, you know, and then call multiply on that times k. Hopefully it's still loaded in some register. So this is a program. And if k equals 2 is given, then we could partially evaluate this function. We could essentially call partial on it. And we would have a new program, f2, that now only takes in u, because we've called partial on k. And the result would be just this simplified function. You know, we've now bound k to 2. So k is no longer part of this expression, or it could be, but it's been optimized out. It's a constant. And so we can see this is just 7 now because k is 2, so k plus 1 is 3 times k. 3 times 2 is 6 plus 1 over here. So this all ends up being 7 plus u. So by binding k to 2, we've got a new program that's now much simpler. It actually is probably fewer instructions, and therefore it's faster. So that's kind of interesting. By partially computing the result of this expression on a single input, we've actually come up with a much simpler and therefore faster program. And I stole this example out of a paper, and that paper called this process projection, the projection of f at k equals 2. The way Python would refer to it is as partial. It's the partial of the function at k of 2. And in this lecture, I'm going to refer to it as specialization. It's the specialization of f on k equals 2. Questions about this partial computation? It's two things. We're binding variables, we're binding inputs, and then we're optimizing the original program such that we don't compute anything related to that now bound input. Okay. So let's see what we're doing here. Specializer, let's say we've got some machine that does this process. You know, in Python, we do. In Python, it's the partial function. But let's say on a higher level now, we have a program that we can pass in a program and it converts it to a specialized version of that program. And we'll call that a specializer, S. And this is the symbol I'm going to use for it. You can see it's kind of a combination of the compiler symbol and the interpreter symbol, and that's because the specializer kind of is a combination of a compiler and interpreter. It partially interprets the program on what data it does have, and it compiles the rest into whatever's left. So it's kind of in between a compiler and an interpreter, and we can see that here. It takes in a program just like an interpreter does and a compiler does, but then it also takes in data just like an interpreter, but not all the data. And it outputs this new function, and I'm going to use subscript to refer to the specialization of a function. So we started with p of ku, and we specialized on k, and now we're left with p sub k of u. So this new function has been specialized on k, but it still takes u as an input. And then some more notation here. Equals means the same as. They are the same. But I'm going to use the congruency symbol to refer to does the same thing as. So maybe these two things aren't exactly the same, but they behave the same. So they're congruent, so to speak. So let's see an example here. Oh, and here's an example of the congruency. P sub k of u is congruent to P of ku. Why is that? Well, if we pass in k to the specializer step and we specialize P on k, then we should hope that we didn't change the program. This program should still do the same thing. It's just now been wrapped up with k. So it should do the same thing as P super ku. It's just here, we've already bound k in. Here we're passing k in at runtime. So we can expect that these programs will do the same thing, but they're not the same because ideally this one is faster. Ideally the specialized version is faster because we were able to simplify the expressions, maybe delete some code because we knew some of the data ahead of time. Questions about this? All right. So let's see an example of a specializer here. We've got this symbol again, and let's just use the example we used before. Here we've got a program, takes in k and u, and then we pass in k, that's the data here, k equals 2. Then we get a new program that just takes in u, and this program would be this. So I'm just taking the example that we had before and putting it in terms of these block diagrams that I'm using here. Questions about this? I have a question here. What language is this program in? The resulting program.
That's unspecified, I think.
Yeah. So unlike a compiler here, a compiler, for the purposes of this lecture, we're mostly assuming that a compiler is going to compile it down to some effectively executable program. But here, a specializer makes no assumptions about what the output is going to be. And in all likelihood, it's going to be the same as the input. So like here, this hasn't made this any more executable from a language standpoint. It's just simplified the expression in the language that it already was specified in. So yeah, specializer doesn't actually make anything more executable. That's kind of important. It just takes what's already kind of a high-level language and it simplifies it, but it's still in a high-level language. So we still need some sort of interpreter or compiler. Speaking of still needing an interpreter or a compiler, let's look at some cool stuff that we can do with a specializer. So we've got a specializer. What kind of things can we put on this left side here? I mean, it takes in any kind of program. And we just said, we still need a compiler or an interpreter to actually do anything, right? What would happen if we put in an interpreter as the program that we're trying to specialize? So we're going to pass this interpreter in as the program input of the specializer. And now what data does the interpreter take in? Well, an interpreter takes in a program. Programs are data after all. And so the data input of the specializer here, we're going to make it a program. All right, so we're specializing an interpreter on a program. And what is the output going to be here? You know, after running this specializer on these inputs, what's going to happen? Well, we know that specializing P of inputs ku on k should do the same thing as P sub k of u. So we should hope that we don't actually change the behavior of the interpreter here. All we're doing is kind of binding it. We're specializing it. So the output of this is going to be some interpreter, but with the program kind of baked in, simplified down, such that the interpreter only knows how to execute what this program does. So we've actually created almost a worse interpreter. This interpreter can only interpret one program, but it's been specialized to interpret that program. And what we're left here is a program now that takes in one input. What was the other input of the interpreter? We specialized the program input, but we left this unspecialized. So this program still is a function of x, still takes in x. What does that mean about this program? Well, it means that this box, this black box here, is an interpreter that only interprets this program. It's effectively a compiled version of that program. You know, if we assume that our interpreter is executable, which it better be. I mean, if it's a worthwhile interpreter, it's probably executable. So that means this entire program is executable. So what we've done is we've created an executable that performs the work of P in this high-level language. So that's effectively a compiled version of P. So what does that mean here? We've got an equivalence. And if we write it down in our notation, we've got the specialization of an interpreter on P is congruent to the compiled P. So that's the first Futamura projection. Questions about this? Specializing an interpreter on a program effectively compiles it. All right, I'm going to take this equation, I'm going to put it up at top because what we're going to do here is build up knowledge that we're going to use in later slides to perform more and more crazy specializations. So remember this, the specialization of an interpreter on a program is congruent to compiling that program. So what else could we do here? I mean, the specializer takes in a program as input and we just put in an interpreter, and that was pretty crazy. But we can still put in any program. You can specialize any program. What if we specialize a specializer? All right, and this could be the same specializer. We could be literally running this specializer on itself. This would be kind of like saying Python 3, Python 3. You know, Python, please interpret for me Python. Now this is a little different because a specializer is not the same as an interpreter, but we're going to specialize a specializer. And any guesses on what the data of the specializer is going to be? Well, like I said, we're going to use these formulas from the previous slide. And so what did we do in the last slide? We specialized an interpreter on a program. Maybe here this time we're going to specialize a specializer on an interpreter. Okay, so let's do what we did last time. We've got this first formula here. Specialization of a program on inputs k and u on k is congruent to p sub k of u. Here the program p is s now, and k is I. So we should hope that this would behave the same as a specializer that's then been bound to I. And that's what we see. The result of this specialization is a specializer that's been specialized down to a single interpreter. And what's the input that we've left unbound here? Well, it's whatever this, what is the input that we've left unbound? It's whatever this is. It's whatever this program also needed to take in. This program took in an interpreter and we've bound that, but it can also take in something else. And what else does an interpreter take in? Or what does whatever else this has to take in is whatever the interpreter needs to take in, which is a program. So this machine takes in a program. That should probably say a function of P. But does everybody see that? We've specialized the specializer on an interpreter, but we've left out the program for the interpreter to interpret. So that's the next thing we pass in. So we've got this machine here, and what happens if we pass in P? Well, we just saw in the previous slide that specializing an interpreter on a program compiles that program. And that's effectively what we're doing here. We've just bound the interpreter to the specializer ahead of time, but it should behave the same. And so this will effectively compile again. So we've found another way to compile this program. And so if we write this out in the notation, we've got S of S and I, then called on P, is congruent to the compiled P. Specializing a specializer on interpreter and then running that on a program compiles the program. Now watch carefully. We've got called on P on both sides of this congruency. What does that mean we can do? We can factor it out. So what do we just see here? By factoring out the execution of both sides of this congruency, we've found that specializing a specializer on an interpreter is congruent to a compiler. So that's kind of interesting. We've specialized a specializer on an interpreter, and that gave us a compiler. First of all, that's crazy. Second of all, that's kind of handy, isn't it? Because compilers are probably better. An interpreter, I guess I never explicitly said it, but interpreters tend to be slow, but they're also easier to write. But if we had a really good specializer, we could take any interpreter, specialize a specializer on it, and then that would effectively compile things. Questions about this? This is the second Futamura projection.
Well, I don't know if you'll know this. Are the optimizations that you get by specializing something similar to the optimizations you can get by compiling something?
Yes, they are similar. They are similar, but they're trickier to write because you don't know all of the data. So you can only perform those optimizations on the data that you know. All right, I think I'm back. Am I back? We specialized a specializer on an interpreter. I can think of one more crazy thing we could try. We could specialize a specializer on itself, right? This is metaprogramming. We run programs on themselves all the time. So let's specialize a specializer on itself. So what the heck is this? This is, well, we know from our first thing, we should expect this thing to behave like how if we had just taken a specializer and just bound the specializer into it in the first place. So the output of this machine should behave like a specializer, but that's already just been bound to the input of a specializer. This looks kind of familiar because this was part of the diagram from the previous slide. Before we took a specializer and we specialized it on an interpreter. So let's put the interpreter in now as the missing input to this specializer. Well, we just saw that specializing a specializer on an interpreter is a compiler. So we know that the output of passing in this interpreter is a compiler. And now if we write this out again in our notation, we see this S of S of I, S of S, then called on I, is congruent to an interpreter. I'm sorry, a compiler. But, before we did this cool trick where we had, called on P on both sides, and we factored out the P. We're going to do that here, but it's not clear what we're going to end up with because we're not executing this compiler. This is congruent to a compiler, but a compiler is just a program. There's nothing we can factor out of that, right? Well, no. If we just don't execute this on an interpreter, if we just factor out this here, what did we end up with? Well, we've got this machine here that takes in an interpreter and outputs a compiler. So by specializing a specializer on itself, you actually create a compiler. That's a machine that outputs compilers. So a compiler is a metaprogram because it reads in and writes code. Compilers are certainly metaprograms. Specializers are metaprograms because they take in code and then they output code. But taking this metaprogram and calling it on itself and itself creates this machine that creates metaprograms from metaprograms. So we've gone up a meta level here. Not only are we writing metaprograms that compile and interpret things, but now we've written a metaprogram that takes the interpretation and creates a compilation from it. So this is a compiler. And so what this means is that effectively any language that we have an interpreter for, we could create a compiler for. And that is theoretically true. Any language you can interpret, you can also compile. And the cool thing here is that a really good specializer would mean that you would also have a pretty good compiler for any language, but interpreters are easy to write. So by creating a single really good specializer, we could have all the compilers for any language that we could interpret, which is a much, it's a much easier thing to interpret. So this is kind of the theoretical singularity. By creating a really good specializer, we open up this entire world of compilers that we couldn't otherwise write in languages that don't exist yet. And what this is actually maybe useful for is domain-specific languages. So compilers, you see those in, compilers exist. So, this has been kind of theoretical. Really good specializers are very hard to write. But people write compilers from scratch. And what they do is they're often used to create domain-specific languages, which are small languages that are designed to be able to frame problems in the language of that problem. And so, an example of a domain-specific language is, I think, the New York Times. If I want to say the New York Times, engineers created a language for the journalists to be able to lay out their news. And that was a domain-specific language. I don't think, it wasn't Turing complete, but it was a language that put the problem of laying out a newspaper into its own terms. And so the journalists could understand it, and then they were able to compile that into actual print. So that's an example of a domain-specific language. And often compilers are used to create them. Very cool stuff. So I'm introducing 3 extra credit write-up homeworks here. These will count, they're out of 0, so to speak. So they will actually boost your grade. And the extra credit write-ups are, what is PyPy? How does it relate to this lecture? It's tempting for me to go into what PyPy is because it's cool, but I'm not going to because it's the extra credit homework write-up. So even if you don't need extra credit, I encourage you to look into PyPy because it's really cool. What are some good applications of partial evaluation and a specializer? Like I said, it's very hard to write. So those Futamura projections are still kind of a dream right now. But there are good applications of specializers. And so what are some of them? And then the last one is, what is Jones optimality and have we achieved it? So I'll just leave these with you guys. I'm out of time. So I'll just end lecture here. I hope this was mind-blowing. Sorry for the interruption. I'll have to stitch this together and for the YouTube video. This was the one lecture that I messed up recording last year. And so I was really excited to actually finally have a recording of this. And then, of course, it's the one where something goes wrong. So that's okay. I think we still got it. So yeah, good luck on homework part 2. I'll hold more office hours this week because this part is definitely trickier. So good luck.